Hello. Yes, first of all, I want to thank the organizers for letting me speak here today. My name, as you heard, is Ned Taylor. I'm a postdoc at Exeter University in the United Kingdom. A lot of this work was done by myself, Joe Pitfield, who you heard on Monday, and Steve Hepplestone. If you have any questions after this, feel free to talk to me or Joe. We both know this about equally. So, I'm going to give you a talk on RAFFLE, our open source code for structure prediction for interfaces. So why do I care about interfaces? Well, as our devices are getting smaller and smaller, interfaces become a larger and larger proportional representation of those devices. They make up a large part of the device, and they also present unique physics that a lot of our modern day devices take advantage of. So they really play an important role here. However, they're also often the breaking point of our devices, be that mechanical, electrical, chemical, or thermal. They're usually the first breaking point of a device. So we have this weird dichotomy where interfaces are both the best part and the worst part of a device. So we really have to understand them in order to figure out how to make better devices for the future. So, however, there's a great challenge with interfaces. Experimentally, they are complex and difficult to really pin down and visualize. Computationally, they are also difficult. They are very expensive to model computationally with ab initio methods. Empirical methods are quite difficult to really describe these things because it requires usually fitting parameters which you don't know what your interface is in the first place, so how can you fit parameters to really understand what this is? They also have large unit cells. So when you're considering a periodic unit, they're usually 300 or more atoms, whereas a bulk system will be maybe 1 to 40 atoms. Additionally, they have a large configuration space. There's a lot of configurations that they can have that could be statistically accessible. So again, you've got a lot to consider when trying to figure out what your interface could be. And this is sort of examples. We have many different varieties of interfaces. We have, for example, very abrupt interfaces, where in the bottom left you can see we have one material, and after about just one atomic layer, we find another material. So there's only slight defects, such as vacancies there. In the top right, we have a sort of intermixed interface, where we start with one material, such as nickel on one side, indium arsenide on another, and in the middle, we have a mixture of them, forming a new phase or a new composition that isn't stable on its own, called nickel-indium arsenide. And then we have other systems where you pin a material between two others, and this forces a new phase for the material that wouldn't exist otherwise. This means that interfaces can really offer a unique environment, be that electronic, mechanical, or chemical, that we can take advantage of to find new materials that we couldn't use before. So I'm sure we're all aware of what structure prediction is. We've been talking about it a lot. In my view, structure prediction really takes on 3 steps. You first of all generate structures. You then evaluate them, be that their energetic properties, their stability through photons, or whatever you want. You then use that information to inform your next set of structures you generate, and you iterate on this process until you've sufficiently explored the configuration space. For interfaces, basically all of this is difficult though. As I said, the evaluation is tricky. They're very expensive to look at or to model, but as we've been talking throughout this conference, there are many approaches that we could use to try and tackle this to cut down the ab initio costs. With machine-learned interatomic potentials, they don't fit well far away from bulk materials, so interfaces they don't work for. But with methods such as fine-tuning or delta models, we can try to address this. However, generation is still a really difficult part of it. As I said, there's an immense configuration space for interfaces. Not only do I have to make a load of different interfaces or structures to try and figure out what it could actually look like, but there's also a large number of atoms I've got to fit into a box. If I'm trying to make random structures, if I'm trying to brute force it, I've got 300 atoms that can all go in a different configuration. That becomes basically an almost impossible challenge to approach. So this is the one that I really want to focus on. This generation, this is the part I want to tackle. And this is why we've developed RAFFLE, to try and tackle this approach. This is the workflow, a flow diagram sort of going through what RAFFLE does, and I'll be referring back to this as we go on. So first of all, what RAFFLE does is you start with a host material. This is one material, an empty region, and then a material above. In this example, this case study that I'll be using to go through, we have graphene encapsulated magnesium oxide. So my host is 2 layers of graphene. And the stuff that RAFFLE will do is put magnesium and oxygen atoms in between to figure out what phase or what form this magnesium oxide will take on. In this case study, we've used density functional theory, PBE, but you can use other methods. The code is agnostic to calculators as long as the calculator properly describes the phase space. We've also heard a lot about the importance of descriptors, how you really need a descriptor that can accurately describe your system or the space you're looking over. RAFFLE uses n-body distribution functions and combines them in a way to make a local descriptor. We choose this because it's cheap, first of all. It is descriptive and analytical, so it's grounded in physical understanding of the systems, and it should mean that this can be quite fast to go through the search spaces. It is also aggregated together, so it forms more of a signature for your systems, telling you what is feasible rather than tell you exactly what system or every atom looks like. For these distribution functions, let's just quickly go through what they are. We've got in the top right a picture of a layer of graphene. We have carbon atoms here, and if we look at the nearest neighbors for a carbon atom, we can see there are 3 at about 1.4 angstroms away. That's what the far left peak is on the distribution function. We then have 6 next to nearest neighbors at about 2.4 angstroms, and that's where the second peak comes from. And that second peak, therefore, is twice the height of the first. So we can build up these distribution functions, and they can describe unique things different from, they can show differences between different materials. For graphene, or for 2 phases of carbon, for example, diamond and graphite, we have a 3-body distribution functions here, and diamond has a 3-body angle of about 100, and diamond has 109, graphite has about 120-degree angles. We then weight these distribution functions based on the relative formation energies of our materials and combine them together to get a generalized descriptor, where you can see here both the diamond and the graphite peaks are still resolved. These descriptors are then used to inform the placement of atoms. But as I make more systems, or I look through more systems in the database, these descriptors evolve over time based on newer structures coming in that are more favorable. So here in this carbon magnesium oxide system, we started out with no data on what carbon and magnesium sort of bonds like. So it starts out, after making 10 structures, it's starting to explore a more covalent-like bonding between carbon and magnesium. We see a first peak at about 1.5 angstroms, and a second nearest neighbor peak maybe at about 3.2 angstroms. As we generate more and more structures, we see that we get less distinct peaks, but we also see these first and second nearest neighbor peaks drop down. They become suppressed to the point of about 500 structures where they're basically not visible anymore. And instead, we start to see these larger peaks, about 2.5 and 3.5 angstroms, starting to rise up. Now, as we get to 1,000 structures, we don't see any peaks below about 2.5 angstroms. And what this is showing is that RAFFLE has learned that for this system, magnesium and carbon like to form a more van der Waals-like bonding rather than a covalent-like bonding. So this is RAFFLE learning as it makes more structures. It uses these generalized descriptors, as I said, to place the atoms. So how does this actually work? Well, RAFFLE does this one at a time. It chooses it takes an atom, it then randomly selects one of 5 placement methods. The first one being just a full random placement as long as it's not too close to another atom. The other option that it can choose between is a void finder, placing an atom in the emptiest space of the cell. Another is a global minimum, placing an atom where it would best fit the distribution function, the descriptor we've already built. One is a growth method where, starting from the previous atom placed, it will look around that atom to find a local minimum and place an atom there. And the final is a random walk where, starting from a structure, it starts in a random place and then walks until it finds a local minima. So these placement methods are all built from some physical understanding of be that kinetic, thermodynamic, or mobility growth methods. So as a quick aside, I've talked about these descriptors and the placement methods, but how do we know if they're any good or if they're doing anything at all? So here we have a test case where we've looked at trying to build bulk diamond from a cubic cell. So we start with no prior information and we compare against random structure search. If we look at the principal component analysis plots on the left, we can see that with random structure search, for unrelaxed structures, it samples far away from the red circle, which is the diamond phase we're hoping to find. But with RAFFLE, we find a rather smooth distribution of structures sampled from the random structure set all the way to bulk diamond, sort of forming a funnel here of smooth distributions of structures being made. And with the energy plots on the right-hand side, we can also see that RAFFLE, after relaxation, has sampled more structures close to the energetic minimum than the unrelaxed structure, than the random structure search. So again, with silicon germanium as well, we can do this, take some atoms out from the gray box and place more atoms, and it keeps the phase, but predicts a structure more energetically favorable than the abrupt interface. For our magnesium oxide structures, it generates a load of structures and basically reproduces rock salt and hexagonal phases, rock salt being the global minimum. But it also has produced an ensemble of structures, which is very important for interfaces. As I said, there are many that could be statistically accessible. Now, how does this compare to experiment? Well, with a TEM image from Vasu et al. In 2016, they looked at this exact system and found rock salt phase, hexagonal phase, and a mixed phase, which is exactly what RAFFLE found. So RAFFLE is producing something like that of experiment in the same ratios. And then just a quick extra part, interfaces allow us to make new structures. At large thicknesses of magnesium oxide, you get the rock salt phase. But at really small thicknesses, you can get a polar cubic monolayer, which is not something that's stable on its own other than through encapsulation. And at the medium phases, you get an intermixing of these phases where both rock salt and hexagonal are similar in energy. So with this, it means that you can make new structures. And whilst we made this tool, we've made it available to everyone. And we think there are many new interface materials that could be used for devices that really needs a whole community behind it to find these possible structures. We can't really do it on our own. And thank you very much for your time.
Thank you, Ned. Thank you, Ned. That was an incredible talk. And I do apologize. I got so invested in your story that I actually forgot to keep time. So I think that's a real testament to your story. Any questions for Ned?
Hello, thank you for a nice talk. I'm wondering, have you thought, or is it possible to, let's say, if I'm doing the search with DFT, at the same time train, let's say, ensemble of MLIPs to speed it up, so to say, to speed up the search?
Yeah, so we've done searches using MLIPs, and some of them, as long as they're accurate within the space, they work. So we used the MACE potential for the silicon germanium, and it worked. But using something like ChargeNet completely messes up and can't predict this. Joe has started using his work on delta models to try and improve the search to see if it can speed it up. Preliminary work says yes, but that's not something we've fully explored yet. But the idea that it creates an ensemble of structures should mean it should allow you to speed up the process even further.
Thank you.
No worries.
Thanks for the nice talk. I had a question about the distribution functions. You showed your descriptor as a function of iterations.
Yeah.
So was this the descriptor for always the best structure at that iteration counter, or is it some kind of average?
No, yeah, it's the descriptor is
this one.
Yeah, the descriptor is we're not trying to, whilst it is useful to find the global minimum for an interface, due to growth mechanisms, you're very likely to get a large set of structures. So this is more of a signature of what your structures could look like and could be accessed, rather than saying exactly what the lowest energy phase would be. So it's not describing uniquely the lowest energy structure, but instead ones that are within thermally accessible bounds, if that makes some sense.
So you've got one global descriptor for the material system.
Yeah. So it's a global descriptor that says this is sort of what you should be fitting towards. Each structure, you can make your own descriptor or fingerprint for it, but then you can compare those two together and say how well does it fall under that? What's the cross correlation of those two functions?
Okay.
One final quick question.
Question. So, do you know how quick is convergence normally? Like, have you encountered like it's very hard to converge?
Yeah, convergence for it. So for something like a bulk structure search of diamond, it appears that RAFFLE is quite a bit faster than things like basin hopping methods. However, this is not built for bulk random structure search, so I'm sure or bulk structure search, so I'm sure there are much better tools out there. For interfaces, it's the fastest method we've found so far to search this stuff, but convergence is a difficult thing for interfaces because of that massive configuration space. You never know if you've fully sampled it. I mean, you can never fully sample it, but you can see over time if you found any new structures after X iterations, and if not, then you've probably well sampled it and your distribution function hasn't changed, so hasn't learned, so probably won't do much more. But like you need to the end of the universe to really say through doing full random structure search if you've done everything.
Thank you.
No worries.
Thank you so much, Ned. Please join me in thanking Ned once again for a fantastic talk.